All right, so we're going to begin with some of our exponent rules. We need to do a quick little review. I'd like you to have a calculator handy for this so you can actually plug these things into your calculator and make sure that you're getting the same thing as I am when we're going through these exponent rules. I'd like you first just to find the exponent button on your calculator. For most people, that exponent button looks like it's just a little arrow pointing upwards. So kind of like that. You may also have an exponent button though that instead looks like x to the y, or some variation on that. Okay, so you're going to need to know where that is and be prepared to put it to good use. So we're going to start with 3 to the 4. Well, 3 to the 4, let's talk about what that really means. What that really means is 3 times 3 times 3 times 3. And I'm going to use dots to indicate that I'm talking about multiplying here. Okay, so I'd like you to actually plug that into your calculator and make sure that you can do 3 to the power 4 on your calculator and get the same thing as me. So 3 times 3 is 9, times 3 is 27, times 3 is 81. So you should get that. You should get 81 when you plug that into your calculator. Okay, and we're going to need exponents for geometric sequences. So make sure that you can plug in 3 to the power 4 and get an 81. Okay, so that's what 3 to the 4 means. It just means 3 times itself 4 times. 3 times 3 times 3 times 3. Okay, so far so good. Probably feel pretty comfortable with that. I imagine you've seen that before. When we get into something that's like a fraction though, like 3/4 to the power 4, what that means of course is 3/4 times 3/4 times 3/4 times 3/4. And we remember our fraction rules tell us multiply the numerators for fractions and multiply the denominators. So I can actually simplify this because 3 times 3 times 3 times 3 is just 3 to the 4. And 4 times 4 times 4 times 4 is just 4 to the 4. Okay, so there is actually a little bit of a shortcut there. What you can do when you've got 3/4 to the power 4, 3/4 is just one term. It's its own term. And if there's only one term in the brackets, then you can apply that exponent to here, and you can apply that exponent to here. You apply that exponent to everything that's in the brackets. You cannot do that if, say, for example, you had n plus 3 to the power 5. You cannot turn that into n to the 5 plus 3 to the 5. That is not correct. Okay? So there has to be just one term. If there's only one term, which 3/4 is, it's just a single term, then you can do that. So 3 to the 4, we already know is 81. 4 to the 4 is 256. So we can divide those, 81 divided by 256, and we get like a long, ugly looking decimal. But we could use that. 0.3164 ongoing. Okay, so our key idea there is that we can take this shortcut of looking at that exponent and applying it to everything in the brackets as long as that is just one term. Next, here is an exponent rule called the addition rule. We'll see this again later in the course, but I just want to take you through this basic bit of it. If you've seen the exponent addition rules before, then you know what I'm talking about with this next one. Can you let me know in the chat? Let me know in the chat if you've seen this before. Because I think some of you may have, and I suspect many of you haven't. So if you've seen this before, where I go 3 to the 5 times 3 to the 4, and I can add their exponents, please let me know if you've seen that before in 10th grade. Okay, so I've got a couple people that have told me they've seen that before. There may be a few people for whom the chat has taken a while. Haley, you've seen that before as well too. Great. Jillian, that sounds kind of familiar. Okay. Dasher, for you, that's a familiar one. Great. Sam, it's somewhere in the memory, you think, but you're not sure. Amory, maybe. Kaylee, it looks familiar. Emmy, for you, it looks familiar. Okay, that's good to know. So for many of you, maybe most of you, you've seen it before, but it might be a bit fuzzy. I bet for some of you, you haven't seen it before, and that's totally fine. That's why we're going to go through just a quick little version of it now, and we'll explore it more in a later unit. So here's the trick. Here's the shortcut. If I've got 3 to the 5, I can write that as, get ready, this is going to take a little while. I can write that as 3 times 3 times 3 times 3 times 3. So that's 3 to the 5. And then I'm going to multiply all of that by 3 to the 4. So that's 3 times 3 times 3 times 3. Whew! So really what I've got is 1, 2, 3, 4, 5, 6, 7, 8, 9 threes. So I can rewrite that as 3 to the 9. And that's an exponent shortcut. And there's some rules that go along with that. You can do this if the bases are the same. Now the bases, when I say bases, I'm talking about that number 3. If this is a 3 and this is a 3, I'm allowed to, when I'm multiplying them, just add their exponents together. Just add their exponents together. So what I did there, if I want to take a shortcut, instead of doing all that work, instead I could just say it equals 3 to the 5 plus 4. And that's 3 to the 9. So if I'm multiplying two things and they each have an exponent and their bases are the same, I can just add those exponents together. Same goes for if I'm dividing them, I can subtract their exponents. But we're not really going to do much of that. We're just going to, for now, look at adding things together because it's useful for this one. So if I multiply two things together and the bases are the same, I'm allowed to just add their exponents. Okay, so that's our exponent addition rule. Here's our last one. I'm going to switch pen colors just so this doesn't get confused. This one's very similar. I see 3 to the n plus 7. Well, I can actually write that using this same exponent rule as 3 to the power n times 3 to the power 7. I basically just did the same thing but in reverse. If I've got something and it's got some exponents and those exponents are being added together, I can transform that into two separate bases, each that have one of those pieces and that are multiplying each other. So this is going to be pretty useful in the stuff that we're doing today. I'm going to add one more thing, and it's negative exponents, because there's one example I think we'll get to today. I'm not sure, but there's one example I kind of want to show you that where we can use it to help us out. So I'm going to scroll down to my last one here, and this is negative exponents. So I've got 3 to the negative 4. If you've seen negative exponents before, and you know how they work, can you post in the chat and just let me know that you've seen it before? Because this is one I'm less sure if how many people have seen this before. So if that's familiar, negative exponents, can you please post that in the chat? You can also just let me know if you've never seen it before. So I'm getting a few people that are saying maybe they've seen it before. It looks kind of familiar, a little familiar, yeah. So we're not going to do much with this for now, but I do want to just show it to you because it'll come up again and it'll be a little useful for some stuff today. Okay, so if I've got a negative exponent, what a negative exponent really means is my term is flipped, my term is inverted. So sometimes people will write things like, if we're talking speed, they'll say kilometers per hour, and the hour is on the bottom. But I can actually give that hours a negative exponent, and that moves it to the top. So basically what a negative exponent does is it inverts the thing that it's the exponent of. It flips it. So in this case, what I'm really saying is 3 is I can write as 3 over 1, right? Because I can write anything as over 1. That doesn't change it. So I just changed my 3 to be 3 over 1. If I want to turn my exponent positive, like turn it to, sorry, not a 5, it's a negative 4. If I want to turn my exponent positive, I can do that, but I need to invert, I need to flip the thing that it's, I need to flip its base. So I can change it to a 4, but I need to flip the 3 over 1 to a 1 over 3. So a negative exponent really means that the thing is flipped the wrong way. It's flipped the wrong way. And if I take the reciprocal and flip it, then I can change that exponent to a positive. And of course, I remember my other exponent rule said I can apply that to here, and I can apply that to here. So this would end up being 1 to the power 4 over 3 to the power 4. So 1 to the power 4 is just 1. 1 times 1 times 1 times 1. 3 to the power 4 is 81. And your calculator can actually do this. If you type into your calculator 3 to the exponent, and then be careful, you might need to use brackets, to the exponent negative 4, you should get a big long decimal. And if you go 1 divided by 81, you'll notice you get the exact same decimal. So a negative exponent just means you can flip the thing and change the exponent to a positive. Okay, we'll see those again, but I think they'll be a little bit useful. Those rules will be useful for today. So those are the rules I wanted to cover. For some of you, that's a refresher. For some of you, that's new. Okay, let's dive in on our big topic for today. We're talking geometric sequences. Geometric sequences. So we talked arithmetic sequences yesterday and today. That's where we're just adding or subtracting a common difference. We call that D to get the next term. Now the one we're doing today, geometric sequences, a little different. Instead of adding or subtracting a common difference, we're multiplying or dividing by a common ratio to get the next term. So that could mean to move to the next term, we multiply the previous one by 3 each time. Or we divide the previous one by 2. Or we multiply the previous one by 1/6. Or we divide the previous one by negative 14. But each time we're multiplying by the same amount, or each time we're dividing by the same amount. So that's a geometric sequence. Instead of adding a certain amount each time, we're multiplying or dividing by a certain amount each time. So here's an example using pennies. This goes along with a really famous story we'll see later in this unit. Some of you may have heard it before. But let's say, you know, I like, it's fall, there's a lot of yard work to be done, and frankly, I can't be bothered to do all of it, like cleaning leaves out of my gutter, raking leaves off the lawn. I got a dog, so you got to pick up like dog poop in the backyard. There's a lot of backyard chores that need to be done. So I'm going to make one of you an offer. I'm going to give you, I'm going to have you work for me for a month, doing all those outdoor backyard chores I don't want to do. On the first day, I'm only going to pay you a penny. 1 penny. Not much. The second day, I'll pay you 2 pennies. The third day, I'll double it again and I'll pay you 4 pennies. And the next day I'll double it again and I'll pay you 8 pennies. Maybe I'll give you a nickel and 3 pennies. Now, I know you're saying pennies, Mr. Roy, where do you get pennies anymore? I got a jar of pennies. And so I'll be paying you 8 pennies. And then I'll pay you 16 cents and then 32 cents. And I'll double it every day. And what would you think of that wage? Okay? So pay you for a month, 1 penny, then 2, then 4, then 8, then 16, then 32, and so on and so forth. I'd like you to tell me in the chat right now, are you going to take that job? Keep in mind that job includes picking up dog poop from my backyard. Are you going to take that job? I'd like you to let me know in the chat right now. Are you taking that job or no? So I'd like everybody in the class to tell me in the chat, are you going to take that job or are you not taking that job? Lakin says sure. Marshy says yeah. Paige is declining. Chris is saying probably not. I didn't make it sound that appealing, I know. Case is saying no. Sam's saying, nah, not taking that job. Haley's going to go for it. Okay. So I got a couple of takers here. Now Dasha says, yes, I want to be rich. Now how does that make any sense? I'm only starting you. Your starting salary on day one is 1 cent. Sam, you're saying maybe if it was 5 cents. Yeah. So let's dig into this a little bit. I still want to hear from everybody. If I haven't, if it hasn't shown up in the chat yet, I'd still like you to post. I want everybody to post, please. I'd like to hear, are you taking that job or not? It's about half and half, it seems. Okay, so 1 penny on January 1st. Now I said I wrote January on here. Really, fall work is better. January is going to be like shoveling and stuff. Xavier's going to go for it. So let's have a look at our sequence and let's do it in pennies, not dollars. So first day is 1, second day is 2, and then 4, and then 8, and then 16, and then 32, ... So what's our pattern here? It's a doubling pattern. It's a doubling pattern. So Dasha, you think you're going to be rich, hey? Well, let's find out. So we've got a doubling pattern, and we say, what's the common ratio? So here's how we do common ratios. To do a common ratio, it's very similar to common difference. And so I'd say, look at my term. I'm going to go for my 1, 2, 3, 4, 5. I'm going to go for my 6th term. So T6 divided by T5. I just divide 2 terms that are next to one another. Is 32 divided by 16, and that's 2. I could instead go T5 divided by T4. That would be 16 divided by 8. That's also 2. And looks like that it's that way all the way along. Oh, sorry, I'm putting that under starting term. I got to move this over. There we go. So that's my common ratio. My common ratio is going to be R. We're not using D anymore. R is 2. And my starting term is just 1. We're also going to call that A still. All right. So we've listed our starting term and our common ratio for this contract I'm entering into with a few of you. Some of you declined, and that's fine. Let's see where we end up. I'm going to throw a screen on here. Let's have a look at our terms, right? So term 1, term 2, term 3, term 4, term 5, term 6. Here's what they are. 1 penny, 2 pennies, 4, 8, 16, and 32. So that's our first 6 terms. Here's another way to look at this. Instead of writing the numbers like that, I would actually like to write the numbers like this. So the first term is a 1. The second term is a 1 times 2. The third term is a 1 times 2 times 2. The fourth term is 1 times 2 times 2 times 2, and so on. So if we have a look at the 5th term, for example, right here, T5, I notice it's got a 1, and then it's got 1, 2, 3, 4 2's. And if I want to write those as exponents, they would look like this. I notice there's a connection. My 5th term has a 5 underneath it, right there, and my exponent has a 4. Same for this one. It's a 6 and a 5 and a 4 and a 3. Looks like the exponent on my 2 is always 1 less than the term number. That's what I'm noticing. It's always 1 less than the term number. So I want to see if we can get a formula out of this and make this kind of general. And here's how we would do it. We know that A is our starting value, and it's 1. We start with 1 penny. I know that R is my common ratio. That's the amount I multiply each time, and I multiply by 2 each time. So for term 1, it's just 1 penny. That's our A. For term 2, I'm multiplying that by 2 to the power 1. On my third term, I'm multiplying it by 2 to the power 2. On my fourth term, I'm multiplying it by 2 to the power 3. So how we can write this is our starting term A times our common ratio R, the thing we're multiplying it by, to an exponent that's 1 less than the term number. Okay, so that's actually going to give us our general formula. I would like you right now to please add this formula you can see in the box onto your cheat sheet. This is our general term formula. Not sure why I have a question mark on there. This is our general term formula for geometric sequences. Things like this doubling problem. Our general term to find anything in there is going to be the starting amount times the common ratio to the exponent n minus 1, where n is the term number. Now, Dasha, you said it's 1 month and a frowny face. So that means you're out, I'm assuming. You're out. I still got a few other students who will do it. And what we're going to do now is we're going to see what those students are going to make on, let's say, the 20th day. So not the last day of the month, but what kind of paycheck do I have to write you on the 20th day? Okay, Dash, you're in. I think you'll be happy with your choice, but we'll see. I'd like you in the chat right now, without doing any math, without doing any calculations, I'd like you to take your best guess. And I think we're going to have answers all over the map, and that's great. I'd like you to write in the chat right now how much you think I would have to pay you on the 20th day. So don't do any calculation. I just want a guess straight out of your brain. Your first instinct. How many pennies am I giving you on the 20th day? What's your guess? Again, no calculations. I'm expecting answers to be all over the map. And you can do it in dollars if you want. Marcia, you said $1,000. Lakin, you're saying $6.70. Carissa, you're thinking 500,000 pennies. So keep those guesses rolling in. And you'll see, as I predicted, our answers are all over the map, which is good. That is exactly what I expected. Now, I've missed some people in the chat. I'd like you to please make sure, if it's lagging, that's okay, but I'd like you to please make sure that you put an answer in. Okay, so we're going to figure this out. Sam, you're throwing some scientific notation at me. That's good stuff. I'm a physics guy. I love scientific notation. Let me fix my screen here. So for our equation, we're going to have to use that. We get to use that, I should say. My starting amount is this one right here. My common ratio is this one right here. Oh, you're taking chem. Yeah. Chemistry loves that too. 1 mole of pennies, please. So it's 6.24 times 10 to the 28. Am I remembering that correctly? something like that. Okay, so let's do our general term for this particular penny example. And then let's see how much we get on the 20th day. So my general term is going to be Tn. That's going to tell me how many pennies you get on any given day. My starting amount is 1, so I'll put that in where A is. My ratio is 2, and then I'm putting it to the n minus 1. Now the question is, can I simplify this? And the answer is, yeah, I sure can. Because anything times 1, it doesn't change. So I could just rewrite this as 2 to the n minus 1. So that means I need to take my day, in this case it would be the 20th day, and sub that in for n. Let's do that right now. So on the 20th day, that's going to be T20. You're making 2 to the 20 minus 1 pennies. So 20 minus 1 is 19, so that's 2 to the 19. I'd like you to put this into your calculator right now and have a look. See what you get. What's 2 to the power 19? So when you plug that into your calculator, you should be getting 524288. That's how many pennies you're getting. So to convert that into dollars, we just need to divide by 100. So that means on day 20, I, your math teacher, am forced to cut you a check just for that day for more than $5,000. On the 21st day, it's going to double, and I'm going to owe you more than $10,000 for that day. On the 22nd day, I'll owe you more than $20,000. On the 23rd day, I'll owe you more than $40,000. So this is just going to keep doubling and getting bigger and bigger and bigger. Right now, I'd like you to figure out what your payday is at the end of the month. So let's say it's a month that has, how many months are in October? How many months? How many days in October? 30 days, half September, April, June, and November. All the rest have 31. So 31. Okay, so let's put that 31 in here and see what we get. I should have known that. That's Halloween. So T31, we're going to go 2 to the 31 minus 1. So that's 2 to the power 30. And Amory's done it for us. It's $10 million. So all those of you who turned down my job offer, the last day you would be making 10 million bucks. The day before that you would be making 5 million bucks. I swear I have this all in my bank account, so it'd be no big deal to pay you. But sorry, those of you who said no, you're out. You missed out on there's a sum of something close to the neighborhood of $20 million. So, sad day for you. 737418. Thanks for posting that, Amory. 24. So 10 million bucks. And then I'm going to do a big like smiley face with like green dollar signs all over. This would be you, and then I would be like this. Tears streaming down my face. Okay, you get the idea. Yeah, so this adds up quick. So geometric sequences, the numbers go up like crazy. Doubling problems are pretty wild in terms of how quickly they add up. And so this is actually an example of exponential growth, right? Exponential growth. This is an exponential growth type of problem. And we'll do more of them. Yeah, lovely art. Thank you. Not so much, but I appreciate the positive affirmation. Yeah, I appreciate the positive affirmation. Okay, so so this is an example of one. These can get more complicated, right? We'll get more complicated patterns. A doubling pattern is about as simple as, that starts at 1 is about as simple as it could be. But if you'd taken me up on this, whew, you're rich. You're rich. I want to go through a couple examples, and then I think I'm going to trim your homework a bit because the stuff I planned took a little more time than I thought it would, and I haven't got through everything I want to, and we'll do some more of this tomorrow. But I want to go through a couple examples right now so you can see how this would be applied to a problem that's a little more complex. So here's our second example, and in this case we're looking at trying to determine the general term and the ninth term for these sequences. Now I can tell they're geometric because it seems like they get multiplied by the same thing each time. So you might just look at this and go, oh, I can see right now just by looking at it that to go from there to there you're doing times 3, and to go from there to there you're doing times 3, and to go from there to there you're doing times 3. But let's actually write this out kind of like formally so we're doing it in a way that we can apply to any sort of problem. So here's how we can check. Let's take one of the terms, let's say term 4 because that's my last one. I'm going to divide that by the one that comes before it. So that's 27 divided by 9, and that gives me 3. And I could check the one before that. I could go the third term divided by the second term. That's 9 divided by 3, and again that's 3. So we can say, okay, our common ratio is 3. And it's positive 3. It gets multiplied by positive 3 each time. My starting value, I can see it, it's right there, it's just 1. So I'll write that in as well. And then I can use those to get my general term. I'll go back to my equation, which is general term, Tn, is going to be a r to the n minus 1. Well, my a value is 1. My r value is 3. So this is going to end up looking pretty similar to our doubling problem. Anything times 1 stays the same, so I can get rid of the 1. And I'm just going to have 3 to the n minus 1. Okay, now let's actually figure out the ninth term. So to figure out the ninth term, I'm going to say T9 is equal to 3 to the power 9 minus 1. So I subbed in a 9 wherever there was that n. So that's going to end up being 3 to the 8. And 3 to the 8 is, if I plug that into my calculator, 6,561. And I'll put a nice little box around my final answer there. And around my general term there, because that's what the question asks for. I want to show you the same sort of thing, but now with one that's a little trickier. This next one I notice is alternating negatives and positives. So it starts out as a negative number, then it's a positive number in the next term, and then it's a negative number in the next term, and then it's a positive number in the next term, and then it's back to a negative number. So what could cause something like this to alternate negatives and positives? Well, remember when I multiply something by a negative, if I multiply a positive by a negative, it becomes, the answer is negative. If I multiply a negative by a negative, the result is positive. So it turns out I've got a common ratio here that's negative. So Sam, you said the negative exponent is inside the brackets. Let me show you, let me go through this, and I think that'll make clear how you deal with something like this. So here's what I'm going to do. I'm going to just follow the exact same procedure I did last time, because I think that'll help me keep it nice and clear. I'm going to say my fifth term divided by the term before it, that'd be the fourth term, is negative 32 divided by positive 16. So negative divided by a positive gives you a positive number. And so that's going to be, oh sorry, a negative number. So that's going to be negative 2. Let's try another one. Let's do my fourth term divided by my third term. My fourth term is 16. My third term is negative 8. Positive divided by a negative gives us a negative answer. Again, it's negative 2. So it looks like my common ratio is negative 2. And if you have a common ratio that is negative, it's actually going to make the sign of your sequence flip back and forth. Positive, negative, positive, negative, positive, negative, positive, negative. So it's going to make that sign flip back and forth, which is what we're seeing here. Because each time it multiplies it by a negative, it's going to change the sign. Okay, our first term we can get pretty easily, again, just by looking at the problem. Our first term is negative 2. So now we're ready to build our general term. So let's do that. Our general term is our starting amount times our common ratio to the power n minus 1. Let's plug in our numbers. Our starting amount's a negative 2. And by a coincidence, our common ratio is also negative 2. Now let's think about those exponent rules. We could leave this here. We could just leave this as you see it and use that, and that would be fine. But I want to use my exponent rules to simplify this a little bit. I remember that if I've got the base that's the same, in this case negative 2 and negative 2, the base is the same, I can actually add their exponents together and merge them into one term using my exponent rules. Now the first one, of course, has a hidden exponent. Everything has an exponent of 1 if the exponent's not written on there. So I can write this as negative 2, a single base, and I can add their exponents together. So my 1 plus my n minus 1. So I'm going to give myself a little more space here to keep working. So my 1 plus my n minus 1. I added them together. So let's simplify this a little bit. We've got 1 plus n minus 1. Sorry, that's a little unclear. I'm going to fix that just to make sure everybody can see it okay. And so 1 plus n minus 1, the positive 1 and negative 1 in there are going to cancel each other out. We'll just be left with n. So this is actually negative 2 to the power n, which is a simpler way of writing what we had above. Simpler way of writing it. I also want to make sure it's clear that this is a 2. There we are. Okay, so we're also supposed to find the 9th term. So let's do that. Let's find the 9th term. We're going to have to sub in a 9. So we'll say t to the 9 equals negative 2 to the power 9. Now, if you plug this into your calculator, you need to be really careful with how you use brackets. You're going to want to make sure that you put brackets around the negative 2, around your base, and then put that to the exponent 9. If you type it into your calculator, like I'm going to write here, if you type it in like this, negative 2 to the 9, your calculator would think that it's supposed to put the 2 to the power 9, but not the negative. So you have to be really careful. That's not going to work. You have to use brackets to make sure that it's doing the proper thing. That it's the whole number, negative 2 to the power 9, not just the 2. That's a really tricky thing that students make that mistake on quite often. So I'm going to try putting that in my calculator. You should be able to get an answer of negative 512. So please check and make sure that you can get that. Okay, so we're going to do some more of this tomorrow. I'm going to trim the homework down a bit, and I'm going to go to Edsby and do that right now. The book chapter that this is from is attached right to today's agenda on Edsby. And of course, you can check the solution set. They're pretty helpful. But if there are questions you want me to take up for the whole class, I'm super happy to do that. I love it when you send me questions. So please feel free to do that on Edsby, okay? But don't check the homework for another, let's say, 10 minutes, because I'm going to go in and edit it and trim it down a bit so that we have a little bit less stuff to cover, because there's some more geometric series stuff I want to do tomorrow. So I'll trim it down a bit so you have a shorter bit of homework to do tonight. Okay, that is it for today. We figured out a new type of sequence. Tomorrow we're going to be having a quiz on arithmetic sequences. And again, the hint I gave you was it's going to be fairly similar to what you saw today in your group work. There are going to be a lot of similarities to what you saw today in your group work, and we'll do that near the start of the period tomorrow. Thanks for an awesome day, everybody. Thanks for doing math with me. I'll ask you to unmute your microphone, give a wave, and say a goodbye to your wonderful classmates. I'll be posting this video shortly and the lesson as well. Take care, everybody. Have a great rest of the day.